Oh, you do first. Okay, sorry then. First talk is by Arthur Baer. He's working for FOAM. And I think he will talk about spatial protocols, proof of location, and their vision of a consensus-driven map of the world. If you have any questions, please try to remember them or write them down, because we will have a Q&A session after each talk. Also, the whole event is being live streamed right now and also uploaded to YouTube afterwards. The camera is right over there. So if you feel uncomfortable with being on film, maybe you can step behind the camera, and I think you should be fine. So without further ado, please welcome Arthur from FOAM. Thank you.
Hey everyone, thank you for coming. I think actually the camera is very high, so you won't be seen even if you're sitting here in front. We're FOAM. We are based out of New York mainly. We're now switching to LA, and I'm sitting here in Berlin. My name is Arthur Baer. I'm the creative marketing director of FOAM. I've been working with them for approximately 8 months. And what we do is we develop geospatial standards, protocols, and proof of location. And what we do basically, and this is what we're building as part of that work, is 3 elements. I'm going to focus mainly on showcasing the spatial index and the proof of location protocol today. But we also developed the crypto spatial coordinate system, which is an open standard for geospatial location bound to smart contracts for blockchains, especially the Ethereum blockchain. The applications of what we're building are of course vast, because as soon as what we're building enters the real world, we have to navigate within it. So if it's from mobility to supply chains, like a gradual supply chain payout system, it needs proof of location, and it needs a way to handle space. The same with location analytics, of course. IoT is a huge sector for it. Geospatial data markets, if you have proof of location, you can prove that the data comes from a certain point of origin and has a provenance in a verifiable way. And of course, insurance is also a big sector for us. I'm going to jump through this quickly, but basically, the cryptospatial coordinate system is a way to index the world and bind locations to a smart contract. You get these cryptospatial coordinates, and you can use them for any application. It's just an interoperable standard that we're proposing, and we're working on it with the Open Geospatial Consortium, which is the biggest geospatial standards organization in the world. So we're very excited about that. But I'm going to talk more about this, which is a way to, if we now have this interoperable standard that indexes smart contracts and has a registry of where they're located, we can visualize them. And this is not how it's looked, but this is what the stack is of the spatial index. As you can see, our team is working, they're functional programmers, which is also interesting. I know that DFINITY just had a big announcement of moving to Haskell. Where's Arthur? That's true, right? Arthur? Is he here? No? Okay. I think that's true. So I think that's we're basically, it's a general purpose web application that can be used for any applications. Any dApp can use it. You can repurpose it. It's open source. It's not tokenized. We're doing it to build an ecosystem around a proof of location protocol. So if you want to build a decentralized Airbnb, for example, this is a pretty easy way to do it. It's built on PureScript, which compiles to JavaScript, and it's built on Mapbox and Uber StackGL for visualizations. I'm going to quickly showcase it. Wait here. Okay, so I'm going to go here because I can only... So this is what it looks like. Wait. This is not optimal. Okay, so this is what it looks like. You have smart contracts that are deployed on different locations. You can pull them up, and this is just a test environment to showcase the general purpose application. And you can navigate between them. And let's say we want to place a smart contract somewhere. We have integrated MetaMask and Uport. and we want to call it DFINITY, for example. Am I spelling correctly? Oh, no, I'm not. Yeah, I have the German, the German keyboard problem. Okay, so we want to deploy that here. Then our MetaMask. We do submit. We can follow that transaction on Etherscan. This is on the Rinkeby testnet. This needs to be validated, of course. And does anyone remember where I put it?
Yeah, on Phillips Street.
Okay, on Phillips Street. And let's hope it pops up soon. What? It hasn't popped up yet? That's not good. All right.
In this page you have to reload. This is not really reloading itself.
It's still pending. Oh, this isn't great. Ah. So there it is, and then we have now DFINITY, yeah, a smart contract bound to a location. This is just a simple showcase of the general purpose app. We're going to use this for our own uses, but we also just, this is a general purpose web application. I'm going to go back into here. So, but what I'm going to talk about specifically is our most kind of ambitious project, our flagship element, as we call it, which is proof of location. It's trying to answer the question if an event or agent is at a certain point in time and space in a verifiable way. And this is a beautiful system. This is what we use today for most of those use cases, the GPS system. The problem is that this is trivial to fake on the client side. So we saw this with Pokemon Go, which is an easy example because people started downloading apps and manipulate their own GPS location. When you have smart contracts that want to execute on geospatial data and location, you need a two-way verifiable location, basically. And yeah, we want to build that, which is the dynamic proof of location protocol. We think that if there's money or value at stake, you need a much higher trust model. So what we're doing is, this is the dynamic proof of location protocol, so to speak, is we're incentivizing the setup of radio beacons that are available in a sync. Similar to GPS, we use 4 nodes in sync that sign messages with a timestamp and then can localize an agent in space and time. What we want is a bilateral, so two-way signing, so that not only as in GPS you know where you are, but also the nodes know where you are. We want to set up economic incentives so that anyone can set up these radio beacons and both get tokens in form of block rewards and in form of microtransactions for giving someone a presence claim. And we want to do it on the blockchain. So how do we try to do this? So the first step is to see what is this beacon. So we have two kinds of beacons, but I'm only going to talk about this one because that makes the whole explanation easier. So we're using zone authorities, which is a radio transmitter, a local clock, which has to be used for the time sync, a public key, an internet connection, and a computational power to maintain a shared state machine. So let's say we want to set up a proof of location setup here in Berlin. This is Trust, down here where we are right now. That's full node, the space in Kreuzberg, where we also have a seat. Up there at the top is my home, and that's a factory Berlin, another space. So you have 4 nodes. This is approximately I'm going to go more into what kind of radio you want to use, but this is approximately also we hope, the distance a LoRa can cover in Berlin. So each of these devices gets put down physically. They stake on a root chain and get a proof of authority and then maintain a shared state machine and a timesync protocol. And I will go more into this. But what happens basically is that if a user enters the zone, as we call it, which is a quorum of staked zone authorities, it has a public key, and it wants its proof of location validated. So what it does is it sends a message to all zone anchors over the radio frequency, over the radio chip. It has to provide a receipt of a staked payment already, so you can't attack the zones by just saying that you're going to pay in the future and then never do it. So what you do is you stake an amount of money on the root chain that will be given to the zone authorities when the proof of location is provided, and a cryptographic nonce. And what happens is the zone anchors receive the message, they note the time, and they share it with the other zone authorities in the zone. Next step is the zone anchors push the time difference of arrival to a state machine log, which we're expecting to work with Cosmos Plasma solution, which basically that the zone is a shared state machine. They push it into the log and back to the beacon. The logs are controlled by an external verifier that check the logs for frauds, and then push a proof of location to the root chain. And here the proof of location contains a geohash with the exact location, a reference to the zone authority that issued the proof of location, a reference to a valid presence claim, so the logs, and a computational proof of the correctness of the presence claim, which was provided by the verifier. And so in our system, it ends with a proof of location system, but we also use other proofs like proof of authority, which is given when you stake on the root chain, on the mainnet, and a proof of sync, which is a time sync protocol that has to be continuously run by the zone authorities by pinging each other. And so this, I want to talk a little bit about that we use 3 different consensus models within this stack. So this is by Dominic Williams, that there's 3 main flavors: synchronous, partially synchronous, and asynchronous consensus. And what we do is we use all 3 in what I just talked about. We use an asynchronous root chain, like Ethereum or DFINITY. We use this semi-synchronous shared state machine in the form of Tendermint and Cosmos Plasma. And we use a synchronous radio time synchronization protocol. And right now, we're in the steps of stress testing this technology, which is called LoRa, which is a certain kind of radio transmitter. It's a low power, wide area network radio beacon, and it has a sweet spot of long battery life and long range. And what's also interesting about it is that it's permissionless to deploy, at least in the States right now, which means that anyone can deploy one of these. And they're small, like a fingernail, approximately. And what's also interesting is that they already have communities around them globally. So this is the Things Network, which is a non-economically incentivized hobbyist group, which exists in many parts of the world. This is their coverage in Sydney today, and this is, again, to underline, without any economic incentives. This is just hobbyists. And this is in Zurich, which has the biggest density of LoRa chips for this. So just to bring this together again, we provide proof of locations through synchronized clocks and triangulation. We do this through low power wide area networks. We use cryptoeconomics and incentivized proofs to incentivize this network, and we use different consensus models to in this stack. And yeah, so it looks like this. You set up LoRa chips. They synchronize their clocks and enter a clock synchronization protocol. They stake, form zones, have an area of local coverage, and then you can provide proof of locations for external parties, and they provide microtransactions for getting a proof of location. So we have a trustless, independent, open, accountable, and incentivized system that enables, as an infrastructure, a large number of decentralized applications to be built on top of it, which is also the reason we're building the spatial index, is to kind of help an ecosystem grow around our protocols, because many systems that will interact with space will need a proof of location protocol. Thank you very much. Yes. I think we have 2 mics, yeah.
This is working.
So just that I understand it right, so basically you just measure the time of how long it took from sending the signal to receiving the signal, and then you compare that to the other 3 nodes who received it as well, and you calculate the vector.
That's how time distance of arrival
So
works. Yeah.
the important part here is that these clocks are very much in sync, right?
Yes, so they continuously need to resync. The zone continuously needs to resync and be very much in sync, which is of course important. And the clocks themselves are extremely important, because you need very accurate clocks to be able. So what we're doing right now is we're working with LoRa and different firmware to try to stress test what is the kind of resolution we can get. Which is, of course, very, very. So that's what we're working on right now.
Like that's in the hundreds of, like the tens of milliseconds, isn't it? Or
I'm not sure exactly, but
low,
I know that it's not arbitrary. It's not a trivial. Yeah.
Exactly.
So there's a combination of 2 things. It's the throughput of LoRa and the clock quality, which are very important to just experiment with and to stress test.
So I can, if I understand this right, so basically if I want to prove location,
yes,
and I'm walking around somewhere, like how much I would ping it. So basically I would ping it as much as I want in order to get the resolution I want, and then pay more because I ping more often.
We don't know yet. I probably, probably will be pretty cheap. In the beginning, nodes will be incentivized through block rewards rather than the microtransactions, because we want to build up a density of nodes. Your transaction cost should be pretty low, we hope, but it's a market. So it's not bound to our tokens, so the zone anchors can get paid in any currency. Potentially they will want stable tokens.
Yeah.
And they decide a price, and you stake that price on the root chain, and then if they provide you with a proof of location, your staked amount goes to them.
And for what exactly is the state machine? I mean, these nodes could just ping each other there to receipts. It's basically to calculate the final position.
Yes, it's to, well, not only it's to, yes, that's how I understand it, yeah.
Yeah. Okay, so basically then the amount of people it can measure is limited by the state machine, what it can process.
Yeah, not only that, but also the radio frequency. So you wanna
yeah, how much people can ping around, right?
Well, yeah. So you also have an upper level of how much radio you can. They start disturbing each other after a while.
Yeah, and is this allowed in Germany? I think it's not, right?
And it's not allowed. So in Germany, LoRa has a cap on how much one device can chirp per day, which is percentual. It's 1% of the time, as far as I know. We're looking at individual regulations. Right now our focus is on stress testing the actual, the resolution. And we're looking at with local communities on what are the regulations of the individual countries. But yeah, sure, it's regulated some among other things here.
I mean, congratulations, looks awesome. I think this is a really great thing to have, and this is exactly the kind of pieces and components we need in order to create like the crazy future we all kind of can see.
Thank you.
Any more questions?
Are there questions online?
No.
Okay then.
Do you want to come here and take the mic, or?
I can also repeat the question if you want.
So you mentioned that the security is obviously much higher than compared to GPS.
Yes.
Can you elaborate a little bit on that?
Sure.
Maybe?
So GPS right now, just it's a really easy way to locate yourself. So basically what you do is you triangulate yourself through the timestamps of a number of satellites. What it doesn't do, it doesn't do two-way communication. So the GPS does not record your position. So it's basically trivial for you today to download an application and say that I am in, I don't know, southern Sweden. What we're trying to do is create, into the two-way communication with the local radio beacons, we create a higher security model so you can't do that.
So you would, I'm just thinking about how to manipulate the system. Would it be possible if you would somehow be able to fake the 4 LoRa emitters?
Well, there's two ways we want to combat that. So the first is if we get a certain density within an urban environment, you always have nodes that will check each other because of the range of the nodes. Then in non-urban environments, it gets a bit trickier because then you might not have the density needed. So we're looking at different incentivization models. So you as a, maybe similar to a token curated registry, you have an incentive to, as a community, weed out the bad actors over time.
Okay.
But that's something we're looking at, but that is a longer term for non-urban environments.
Sounds good.
Thank you.
Yes? If you want to, I can repeat, or?
So the actual concept of proof of location, I guess it totally makes sense, even for someone who's not that into technology like me, let's say, all right? Can you maybe give us an example of an app, or let's say a business in general that that might want to take advantage of that technology, and why they would choose your technology over another one?
Okay, so we see, I'm going to do a few ones because it's, first of all, we don't really know yet what kind of verticals will be possible through provable location. Right. This doesn't exist today at the scale. What exists is two systems. The first one is short distance, basically Bluetooth handshakes and stuff, which they use in, if say I'm repairing an electronic box and I want to prove I was there, I can do a handshake with a Bluetooth device. That's a secure transaction, a proof of location, but that doesn't scale. And the second one is GPS. So the first thing we could do is Pokemon Go, but the Pokemon have real value. Right. Because you wouldn't be able to manipulate the GPS. The second one, it gets a bit more interesting. You can write smart contracts for supply chain payouts. But you wouldn't have to control, you could do gradual payouts over time based on the distance rather than lock up the money during the whole transaction, which would mean I don't know how many $1 billion will be freed up globally. That's one, like, there's a lot of possibilities that I don't know. One more is IoT devices. I want to sell data on a geospatial data market. So I have a thermostat. And for someone, this thermostat data might be really interesting. But today, there's no way to validate, trust me as an individual, that this thermostat data is actually not simulated on my hard drive. Right. So what you can do is you can stamp the thermostat data with the proof of location, and therefore you can open up a market for data that wouldn't be possible otherwise, because you now have a new trust model for the origin and attribution of that data set.
And can you maybe give us, let's say, a very concrete example? Can you think of an actual company which might say, hey, this is actually exactly what we're looking for, or this would help us a lot in our everyday business? Can you think of a... Amazon,
Google, Airbnb, Uber? I don't know.
Right. I've heard of them. I've heard of them.
What?
I've heard of them. Yeah.
Yeah. Well, I don't know. I think it's both. It could be an advantage to existing companies, but we also see potentially other companies growing out of this that we can't think of yet.
Right.
So what the idea is, and I have the previous slide, is that that this kind of other stuff grows out of it. But yeah, I hope that the existing players within the scene also can use it and want to support the system.
It would be huge for logistics companies.
Yeah.
Because logistics companies
Yeah.
often have responsibility to
Cool. Thanks.
So should we do the mic, because I think people online can't.
I was just thinking about like you having a shipment and you pay like half, and then the boat almost reaches the harbor, then sinks, and you paid like 90% of the shipment.
That's it.
It never actually arrived.
Yeah, that's a, yeah, I don't know. So I'm not saying,
it sounds like a great
I'm
idea.
not trying to sell you a shipping, a boat application on this. I was just using a reference, yes.
Yeah, I mean, it's actually a great idea. The thing is, what I can think of, because you were asking about examples, I mean, you know, we will see blockchain commercialized in the next few years. And for example, I'm project right now, what I'm doing is a fashion blockchain. And here the use cases are exactly great for that. So you want to have people go to a place and there's a proof that they were there, then they maybe receive some special rewards or access.
A non-fungible token or something.
Or discounts or whatnot, just because they pass by a window or something like this. So I mean, I think this has unlimited potential. Yeah. Or for example, you picked up the trash and you can actually prove that you walked to the place to put it there, you know?
Yeah.
And then you get rewarded.
We had
for that.
someone pitch a dog walking company, I think. Yeah. Oh, yeah.
I think you one question. Can you elaborate a little bit on the role the verifier is playing?
Sure. So I must say, this is again, this is the first time I do a presentation that goes into a little bit more technical depth. I don't have a developer or engineer background, but so what we're doing is we're comparing the we're running a thought loop on the different timestamps of the zone anchors, and verifying that the triangulation pans out as an external party, verifying the data set basically. And then that needs to happen before it's stamped as a proof of location.
Seems to be a little bit of a centralized part in
you mean the
this entire
verifiers?
mechanics
So
on
the
that.
verifiers are not foam based. They are basically, you could call miners within the system that contribute computational power in return for, and have to stake in return for microtransactions. So a small transaction of the. So they're not. It's not foam controlling. We're not verifying the transaction. It's a totally decentralized system in that way. Yeah.
Thank you.
Thank you for pointing that out.
Hey, so I want to ask a question about spoofing location.
Yes.
So you said that the proof of location depends on the fact that there's two-way communication, in that the device receives signals from the beacons, but also sends something towards them. So my question is, what prevents somebody from deploying one device to an actual location, but then again having a different device somewhere else, and then relaying those wireless communications between them, and then by having device B be in a certain place, actually misprove that device A is there?
Great point. So it's basically a proxy question, right?
Yeah.
So that's a tough nut to crack. We're looking at attestation, so both unique identifiers and attestation over time. But yeah, we're looking at that. I don't have a good answer for that right now. But it's a good point.
Could you tell us a bit more about your team? How many people are working on the project?
So I'm the only one in Berlin. We have, I think, about 10 people in New York working out of Brooklyn Navy Yard at a co-working space called the New Lab. We also have other developers in Europe, one in Hamburg and one in Spain. So we're around shifting between 10 and 15 people, I would say.
And do you have like a time frame for, you know?
So that's a tricky question, also from a let's say legal side, because I think what we're doing is, so our time frame is very much based on how much the community will adopt this and how much we can try out in a short time frame and test parameters before enforcing staking and slashing conditions and being able to deploy this system, especially on the mainnet. Because we're going to need a lot of testing before we want to push this out. We hope to have, by the end of the year, at least local community groups that have deployed LoRa's, and I want to set one up here also, so we can have a testing environment both for developers and also for ourselves to do parameter twisting.
Thanks.
Yeah, there's one more question.
I think this should be the last one.
Thanks for the presentation.
Thank you.
I have a question regarding the incentives. So I see that your system actually competes with Google, Google Maps, right?
Maybe.
In a way, okay. Let's say let's take this as a hypothesis.
Yeah.
And for instance, Amazon would be one of the early adopters of that technology, right? Because they have incentives to use foam, right?
Well, they could also build their own centralized solution if they get enough density. But yeah, sure.
Okay.
Yeah.
But then, like, Google and Amazon are interdependent, right? So, do you see at some point like a conflict of interest evolving?
That I don't want to. I don't know. I'm not sure. So you mean if we cause a chasm between Amazon and Google because of foam? Yeah. I can't speculate on that. That's a great maybe, but I don't think we're going to break up Google and Amazon's relationship any soon with this technology.
I hope though.
Yeah, well, let's see. I don't know. I can't. Yeah. Oh yeah, I think that's a good last question, maybe. Yeah.
Yeah. Yeah. Thank you for the great talk about a great project, in my opinion, at least. So, thank you.
Thank you.
So next up is DFINITY's Arthur Baer. He's Director of Communications, and he will probably talk about blockchain scaling solutions, blockchain governance, and also our vision about a decentralized cloud. So please give him a warm welcome.
Thank you, Moritz. I did send you the presentation. Actually, it's on your computer.
Okay.
Yeah.
Did you send it to me via mail or?
Yeah, Gmail. It's in a Google Docs format. If anyone needs to stretch their legs or grab another beverage, now would probably
Yeah, grab something to drink if you want. Good time.
You need a clicker?
No, I'll just use the laptop if you want to leave it there.
We'll do this, and then this, and then this. Sign in.
Oh, shit. Oh, do I have to sign in?
Yeah.
Oh, damn. I'll reset. Two, two, one. Howdy, folks. If you're just about ready, we might wrap this up and plow through this stuff one more time.
I'd be worried.
Yeah.
Just double check when you start if people just ask if everyone in the back can hear you.
Oh, good idea.
So, we are starting again. And yeah, again, welcome, Arthur.
All right, thanks for the warm welcome, Germany. Well, yeah, good to be here. Thanks tons to Arthur of the Foam Space team for kind of hosting this little get-together. Hugely appreciated. Great presentation, and Foam is a really amazing application as well. It's like one of the coolest blockchain applications, I think, that have actually emerged and managed to persist through the years. It's really amazing to see. And great to see such a solid turnout to a DFINITY meetup, which is the inaugural. So I'm Arthur as well, which is it's not often that I actually find myself saying that. I work at DFINITY and I'm mostly involved in communications. I used to make podcasts. I wish I actually still did. I'm going to try to kind of get back into that. And I've always been kind of looking at the blockchain space and trying to figure out where it's going to go and what are the dominant design paradigms or what are the dominant design choices that we're going to see provide a competitive advantage to different platforms to allow them to move forward and succeed. And DFINITY has made some of the best choices, I think, or all of the best choices, in my opinion. And that's why I actually joined the team. So this presentation specifically, first of all, it's full of a bunch of new stuff. It's a bunch of old presentations kind of chopped together. The idea is I just want to give a full kind of coverage explanation of what DFINITY is, or at least kind of the vision of DFINITY. I want to identify a problem that exists today that's pretty obvious, I think, to everyone, and that's the frailty of our information infrastructure. I want to talk about WebAssembly, and for you there, Frank, and kind of what it is, and then what we can imagine might be possible now that we have this new infrastructure piece called WebAssembly. And then I'm going to talk about, dive straight into the technical stuff and talk about how DFINITY generates randomness and why it's so great. And even though these are somewhat non sequiturs, they give a good explanation of, or a good kind of broad picture of the reason for DFINITY's existence. I usually like to refer to my slides a lot, so I'm going to have to actually crane my neck a bit here, but bear with me. So for today, we're going to start off with the need for new global business infrastructure, the emergence of this new computing paradigm, WebAssembly, and how this might relate to something we might call Cloud 3.0, what WebAssembly and blockchain might make possible, the importance of randomness, and then how we generate it. So I think it's kind of a truism to say that global information infrastructure is frail. But to really understand it, if you think about the choices that you make when you set up your hosting infrastructure, and then you think of the consequences of those choices, none of them are appealing. No matter what you do, your data can be stolen, and your infrastructure may collapse, right? Or may break down at some point. And that means intermittent service provision for you. And it's certainly suboptimal. And so if you outsource to, say, Amazon Web Services, which has a pretty good record of uptime, you know you're still going to have some downtime. You know your data still may be stolen and your system penetrated. But you also know that Amazon Web Services may choose to just deny you service at any time, leaving you without this critical partner. And this is a business dependency. And one of the clear kind of choices in the way that we define business in the future is not relying on other businesses to allow us to do business. And again, when I say business, really this could be the provision of any service that any of us use. All of these things rely on a network of organizations to provision. And the more organizations that are required to provide that service, the more frail or the more intermittent we should expect that service to be in terms of its availability. And then finally, if you choose to use an external party to completely provision part of your business, classic example would be email or payments, you know that they're going to scrape all that data and use it for their own nefarious purposes, as we've seen with Facebook, PayPal, etc. And you get all of those service interruption risks that you get with a business dependency, as well as all of the risks of downtime and data theft. So no matter what you choose today, there's just no good option available to us. And I mean, we can see this in the kind of a list of infrastructure problems that we've seen over the years. So in 2011, someone just screwed up an upgrade at Amazon and it knocked out Amazon Web Services for 5 days for a lot of people. And that's like, this is ridiculous. You know, the internet was supposed to be a network or a communications network that could survive nuclear war. And now someone makes a mistake with an upgrade and the whole thing goes down. Not the whole thing, admittedly, but a lot of services went down for 5 days. Global Payments, which is very similar to PayPal, they lost 1.5 million credit cards. Not their customers' credit cards, but other people's customers' credit cards. Cambridge Analytica, obviously, they scraped data from a business that no one knew who Cambridge Analytica was. No one knew that Cambridge Analytica was surveilling them, but they were a for-profit business, literally using your data stolen from Facebook or scraped from Facebook, which had poor data protection facilities itself, for actually just baked into its user experience, for literally nefarious purposes, for rigging elections. Now with the data protection regulation in Europe, you know, data's become radioactive. It's a very dangerous thing to handle, so it's even more painful if you want to actually host your own data. Storms in Sydney, by the way, in 2016, knocked out AWS services for 10 hours again. So, I mean, there are tons of examples of this, right? But the fact that this network that was built for nuclear war can be knocked out by human error for days or by just a storm in Sydney, it was catastrophic flooding. So that's a bit unfair. But nonetheless, its information infrastructure is extremely frail. Yahoo lost everything. We all know that. And Maersk, this is kind of a bit more of the logistics applications or the logistics significance of frail infrastructure are really kind of apparent. When you think that Maersk was hit by ransomware, Maersk is the biggest logistics operator in the world. They're the biggest shipper in the world. And they lost all of their entire computing infrastructure to ransomware. And they had to reinstall 45,000 computers and a bunch of servers just to get back online. And that 10-day outage, the 10 days, amazing they could do that in 10 days, but that it took to do that cost them $300 million and completely disrupted global trade. A lot of us didn't notice because we didn't have anything in the mail at the time. But if you did, and it was on a Maersk ship, it got lost. And it would often took weeks or months for that cargo or those consignments to be recovered. So that's just the internet. How about businesses, right? How about banks? So SWIFT is how banks communicate. And it's just getting hacked left, right, center. So between 2015 and 2016, there were a series of hacks conducted by some hackers that were really testing SWIFT and finding vulnerabilities in it. They tried to make off with $1 billion over the course of 3 different hacks, but due to a typo for their big heist, they only got 100 million. So also the NSA, we've learned recently, due to leaked documents from the NSA, from their frail information infrastructure, they are also surveilling Swift themselves. Swift just keeps getting hacked, got hacked this year as well. Some of this is actually user error, but there's a sense in which UX is the responsibility of the service provider, especially if you're talking about financial services. And just to really hammer it home, in 2020, this particular research institution thinks that data leakage and data theft is going to cost the world $2.5 trillion. And that doesn't include things like Swift or what happened to Maersk, right? This is just data leakage. So the situation right now is catastrophic, and we need, it's like this total disaster scenario that we've all learned to live with. It's completely bizarre and wonderfully summed up by Vinay Gupta with his term, let's see, maybe I've got that on another slide. Well, here's a great term called the black elephant. That's these black swan events that can happen, but that we all know can happen. We just don't want to talk about it. It's an elephant in the room that we don't want to discuss. I'm sure I'm going to find that heading on an upcoming slide. So we need a new infrastructure that does not fail due to ransomware, is not controlled by gatekeepers, won't fail due to human error, and does not expose data to theft or surveillance and cannot be manipulated by an attacker. It's obvious, right? But at the same time, it's hard to imagine where this is really going to come from. I mean, no one's really talking about completely re-architecting the internet, right? Well, not quite right. And this architecture must be, or this infrastructure must be automated so there are no people involved. It needs to be replicated so that it has no central point of failure, and it also needs to be decentralized so that there's no opportunity for a userless intermediary to insert themselves in there as a gatekeeper. So that's the problem statement. And I mean, I think we can all agree that this is a really major issue and it's something that we should all be looking at. But it's interesting to go around and ask people, like, how many people are actually actively trying to solve the problem that I've just described, right? I mean, does anyone know anyone who's actually saying, hey, we need to completely rebuild the internet or provide a completely new security paradigm for the way that we communicate? I mean, it's unbelievable that this is going largely unaddressed. But we'll leave that there for now and talk about WebAssembly and how that assembles itself, how that relates to Cloud 3, or what we might imagine Cloud 3 might be. So this is a slightly different slide because I need to fit a lot of logos on it. WebAssembly is a new execution environment, or compilation target is another term you might use, co-designed by Apple, Google, Microsoft, and the Mozilla Foundation. And the idea was, let's create a new standard for the web so that you can write in any software language, any programming language, an application that will run in any browser. And quite quickly that said, why don't we just come up with a standard for all computers so that all computers are the same, so that we no longer have iOS and Android. We no longer have Windows and Mac and Linux. Why don't we just have one thing? And so they did that. And we now have available in all browsers today a single solution to all, a single compilation target, a single execution environment in which any application written for that particular environment can run. And this is really where we can expect, the way that we can expect all software to be written in the future. It allows us to do really amazing things, like instead of using JavaScript to write say a payments application for your web page, or connect a form to a database, you can now use something extremely robust like Haskell, say, or some formally verifiable language. You can run it on any computer or phone, and wonderfully, and especially relevant to the blockchain ecosystem, it's sandboxed and deterministic. So its behavior is always understood. It will never behave in a strange way because of a different computing environment, say different underlying hardware. And that's really important if you want to be able to verify the actual output of a program that is run on multiple computers in a replicated fashion. And this is one of our requirements for this new infrastructure piece. So let's imagine now that we have this completely agnostic programming interface, or this completely agnostic execution environment. What this now lets us do is write one program that can run not only on your phone, but also in the cloud, and literally share resources between these two environments. So say, instead of having an application downloaded on your phone, you just had a little icon and a pointer to where that application lived in its cloud hosting. And then what we can do quite wonderfully is every time we open the application, download an interface that is likely to be a new one or an updated one or one that's been improved by UX experts, and actually connects to a new, more advanced, possibly updated application in the background without us ever having to worry about updating ourselves. And this is one of the most kind of compelling visions for a new application and programming paradigm. And you can imagine that this gives us the ability to host or perform the extremely heavy computation in the cloud, while our kind of measly little processor on our phone just deals with the graphics display, and our storage just handles kind of critical user data or login data. And yes, and one of the benefits we can imagine, of course, is never having to update an app again. But now that we've got this, what about when we want to actually use what if we want to use something extremely robust, something that we need to have these qualities of 100% uptime, something that is automated, something that never goes down, doesn't have human error in there, something that's decentralized, that doesn't have an intermediary that might shut that service down. What if we want to use one of these mission critical applications? Well, we need a more robust backbone than this cloud infrastructure that we've already identified as unreliable and insecure. And so this is where a hypothetical infrastructure piece might come in. And this is kind of, because we now have the ability to use WebAssembly as an actual on-chain execution engine, we can use that as a way to split a program between two different execution environments, but maintain a single runtime environment. So it's like your phone is half phone, half blockchain computer, or maybe more realistically, a third phone, a third cloud, and a third blockchain computer. And we can actually assign the tasks that are most important to these particular execution environments, but really this is one giant runtime environment. And one of the beauties of this is that over time, if we can get this decentralized infrastructure to be sufficiently efficient or sufficiently high performance, because it doesn't rely on people to maintain it, eventually, due to the fact it's completely automated, we may get to the point where it is actually cheaper than cloud hosting itself. So that's this idea of the cloud 3, this decentralized cloud, the single runtime environment that encompasses multiple devices, multiple form factors. But really, to understand how DFINITY works and how DFINITY can offer such or can assume to be able to offer such an impressive feature set, we need to be able to generate randomness. And it's important to really understand what randomness does for these blockchain computers. Right now, think of blockchain, right? Think of Bitcoin, right? So what does proof of work do? Like, what does it give us? It gives us the ability to make a claim, right? That if you were the block creator, you had to do a whole bunch of work to take on that role. And there's absolutely no way that anyone or that you could have cheated in order to produce, say, a block, or to take the role of leader of the network. This is kind of the critical value of proof of work. It's how we secure the network against Byzantine or bad actors. But it consumes all of the energy of Ireland to do that. So if we can agree, instead of having to do this whole big proof of work thing, if we can just agree that we have a source of randomness that no one could manipulate and no one could predict, then we can just agree that no one could have possibly cheated, provided that we all agree on the way that the system uses that randomness to select a leader. And that is kind of the magic of DFINITY and the way that it can produce extremely high performance and extremely cheap decentralized computation. Because we get what Bitcoin pays for through the same energy costs as the entire nation of Ireland for free. All because we just figured out how to generate randomness. And this is what really attracted me to DFINITY when I first discovered it. And I think that this is the major edge that is going to give any future blockchain platform the ability to survive in kind of the next generation of the next iteration of these networks. So just to piece this puzzle together again, we've got WebAssembly, we've got this decentralized blockchain infrastructure that's automated, it's replicated, and we've got randomness. And this gives us our trifecta, almost a holy trinity of tools with which to build this infrastructure that will enable us to serve this unbelievable problem that exists today, and that is the absolute unbelievable frailty of our business systems and our current information infrastructure. So does this make sense to people? Is this kind of gelling with other people's experience or ideas? Do we have any questions at this point? Because what I'd like to go to next is just dive straight into generating randomness, which is I love, but it's super technical and it kind of leaves this portion of the vision behind. Okay, I'll just grab a drink of water and we'll get straight into it. So, generating randomness. This is it. This is the magic. How many people here are familiar with asymmetric key cryptography, public key cryptography? A good portion. Okay, so I did this presentation at a place where in Rotterdam, and maybe 3 people put their hand up, and at the end, lots of people said to me, hey, wow, I actually understood what you were talking about. This is amazing. So I'll try and go slow and interrupt me with a question if you have them. This is kind of easy stuff, but it's just it's weird because it's abstract. So obviously, for those who aren't familiar with it, the way that I like to think of asymmetric key cryptography is, imagine you have a key, or 2 keys, right, for a door. One key locks it, the other key unlocks it. You can give anyone the key to lock the door, provided that you're the only person who has the key that unlocks it, right? I mean, that's a pretty simple pretty simple principle. You're the only person allowed in. Who cares if it's who cares? Provided no one else can get in there, then that's great. And so with digital keys, we can do this with encryption, but we can also perform another function, and that's digital signing. And the thing about digital signing is you have one key that can sign a message and another key that can verify that signature. Now, you can give the verification key, this is called the public key, to absolutely everyone, right? It just doesn't matter. They can't do anything with it except determine that yes, indeed, this is a valid signature, right? Who cares? This is great, actually, provided no one can sign it except for you. And this is, because, of course, if someone could sign it, then you wouldn't know if the signatory was you or some other person who had this potential key. And this gives us the ability to use this asymmetric key cryptography to make interesting claims about things online. I mean, this is how HTTPS works. It's how all security works on the internet. So threshold signatures are very similar. The only difference is that instead of having a single, just solid private key, you still just have one, but it's split up into a bunch of pieces. In this particular example, it's split up into 3 pieces. And you need a majority of those, each of those pieces can sign a piece of data, but we need a majority of the pieces of the signature to be able to create a verifiable signature. And so the important dynamic here is that it takes a majority of the signatories to collude to create a verifiable signature. A single signatory can't do that on their own. So in this simple example, right, we take a piece of data, we take a private key, we sign the data. In the case of the threshold, the threshold signature, we wind up with 3 different pieces of a verifiable signature, each on their own, completely meaningless. These are just pointless, useless pieces of data. But if we can combine 2 of those together, 2 of those 3 pieces, we can create a verifiable signature. And this is the magic, right? It means that you can have imagine a board or a jury. So you've got a jury and you need a unanimous verdict. This would be a different threshold of certainty. You need a unanimous verdict in order to convict someone. And you want to digitally sign a document, a digital document, that has the verdict on it. And say you get your 11 signatures, but there's just one holdout and they never sign, then that validatable signature will never be able to be created. It will be just the same as if no one signed at all. And this is the magic of threshold signatures. But they have one more trick up their sleeve, and that is that no matter which group sign, you still wind up with exactly the same signature at the end. And that is really pretty tripped out. The idea that you could have, provided you just have more than half of these participants, each of which have a weird different part of the signature. It's all random, jumbled, it looks like just total randomness. It's gobbledygook. But you put it together and you get this, the same signature no matter what group. It's pretty amazing. And this is at the core of how we generate randomness. Is this making sense so far? Do we have any questions?
How do you make sure that it turns out the same signature at the end if it's 2 pieces of randomness combined? Then they turn out the same?
So the question is, how do we make sure that the output at the end is the same no matter what? Well, it's because this isn't truly randomness, it's pseudo-randomness, and it's derived mechanically through this process or through the cryptography, and it's just magic. Really, it is. It's just magic. As far as, unless we have cryptographers here, it may as well be magic. It's, but it works every time, So, really though, it's just through the mechanics of the cryptography. So in DFINITY, the entire way, or the entire idea behind DFINITY is let's use threshold signatures to create committees that sign as a group, and that we only ever need a majority of that committee to sign, and that gives us some of our Byzantine threshold qualities. It also means that we can tolerate up to just less than half of the network ever going offline at one time. This gives us the ability to make these decisions as the quality of these threshold signatures, kind of like a jury, or kind of like a board of directors. But it also allows us to use that group to create randomness in order to select a subsequent group, so that no one could ever know in advance who was going to be in the next group. How we do that is a little bit trickier to explain, and so I'll explain it twice. Once just with text, and once with a nice, pretty graphic. So let's say we've just got a bunch of randomness. Who cares where it came from? We've just got some randomness, right? And we want to select some members of our entire node pool to participate in a governance decision or in a validation procedure, right? Say they're validating a block, for example. Well, we want to be able to make sure that no one could anticipate that they were going to be one of those participants. So we need randomness to select them. So we do that, and let's take that randomness for granted. That committee runs something called the distributed key generation algorithm that gives them all a share of the private key. They then sign the randomness that selected them using their pieces of that private key. And then they share those signature shares around until they've assembled a majority. In the case of DFINITY right now, what we're looking at is 400 committee members and 201 signatures required for a majority. That new complete signature, which no one could have predicted and no one could have manipulated the creation of, is used to select the next committee. And then the next committee runs a distributed key generation algorithm. Then they sign the randomness that was used to select them, gossip their pieces around, and then use that piece of randomness to select the next committee. And so this system can carry on ad infinitum without anyone being able to predict what's going to happen or be able to manipulate the output of this process. And all because, basically, you know, ciphertext is just all jumbled numbers. It's completely unpredictable what it's going to be. There's no way to anticipate an output from an input without actually running the actual machine, the algorithm, the mechanism. And so we can visualize this here. So we start with some randomness. This is used to select a committee of 400. That committee of 400 signs the randomness, creating the random beacon that selects the next committee of 400, a majority of which signs the randomness, creating a new random beacon that selects the next committee of 400, creating the next random beacon. And this is just the simple, it's phenomenally simple. It's kind of like proof of work, really, really simple, but at the same time, it gives us something proof of work doesn't, and that's free randomness. It's, for me, like, understanding this was, like, it just totally, like, blew blockchain, like, wide open. So is this making sense? Do we have questions at this point?
So if you have the same group of members in the committee, would you get the same randomness twice in a row?
You would. If you have the same committee, right, of course, thanks. If you have the same members of the committee, would you have the same randomness twice in a row? So a lot of this comes down to the actual mechanics of the distributed key generation algorithm and how this works. And I'm not fully familiar, but just in the way that I've described this, if the randomness was the same, yes, you would, if the randomness used to select them. If by some crazy chance a different random beacon selected the same committee, then no, you wouldn't have the same random output because they would be signing a different piece of data to begin with. So you would have this slight difference in the input that would give you a completely different output that no one could have possibly predicted. So it's like, yeah, quite magical. But if you do the same thing, you always get the same output because this is deterministic. Technically, this isn't randomness. Technically, what we're talking about is pseudo-randomness. It's even better than randomness. It's like primo because you can have like kind of a piece of randomness that someone gave you and just said, trust me, it's random. But what we get from threshold relay is we have this deterministic pseudo-randomness that's verifiable because we can see all the inputs that went into creating it, and we can kind of see that it all validates the whole way through. And this gives us something far more valuable than just a claim to a source of randomness. It gives us something we can verify as truly being unpredictable and unmanipulable. And we can use the same committee to sign blocks. This is probably quite self-explanatory, right? A block can be propagated through the network. Each member of that committee, before they discharge from duty, they can sign and gossip a block around until they get the full number of signatures required to add it to the blockchain. And so, let's see, this is it running. This is, on average, we're seeing half-second block times. So, I mean, it's completely amazing. This is our random beacon here. And this random beacon can be used to drive any kind of application, like a gaming application that requires randomness, say a gambling application. Anyone who's trying to build gambling applications on Ethereum right now is having a really hard time because they're having to use block hashes and things like that, these weird imperfect solutions. And we can see the speed at which these recent blocks are popping up. And you probably can't see this number here. It gets about as low as a third of a second. But you do get these spikes. And that's quite undesirable if you want to have a reliable system, right? It would be nice if this was always going to be the same, no matter what, this block time. And because that's desirable, when we actually release the production network, we're going to slow this block time all the way down to 3.5 seconds. And that gives us almost perfect uniformity. And if you contrast that with a proof of work solution, where you have a Gaussian distribution that gives you no guarantees of the exact time you're going to get for a block, that's actually really, really annoying. It's like, oh, it should be done any moment now, right? I mean, we just had that experience with the confirmation of the transaction in your demonstration, Arthur. With DFINITY, you don't get that. It just works. It will work in 3.5 seconds every time. And this is going to give me grief now, isn't it? Here we go. There we go. So, just to look at DFINITY again, it can't fail due to ransomware because it's highly replicated and user accessed. It's not controlled by any gatekeepers. It's an open, permissionless network. It can't fail due to human error because it's fully autonomous. It does not expose the user to data theft or surveillance. I haven't talked about privacy at all during this talk, but there is a whole talk. I bet you can see there's a whole talk to be done about all of these subjects. And there's a whole talk we could do about privacy. It can't be manipulated by an attacker because there's just no way that an attacker could ever predict that there would be in one of these validation committees more than kind of twice in a row or even once. In fact, I didn't mention this, but we get finality, transaction finality, after 2 blocks. So in the demonstration just that it has shown, we have better than Bitcoin in 1 second with our current system. We're going to slow this down, so at 7 seconds, that's fine. And it is structurally robust. So you're not going to have these outages due to bad weather in Sydney. So that's the talk for this evening. You can find me there. We're looking for jobs. Or we're looking not for jobs. We've got jobs. we're looking for prospective employees, and you can follow me on Twitter. That's actually my secure scuttlebutt. Yeah.
Moritz went and got pizza, so I'm going to take over the Q&A. Are there any questions? Do we have any questions online, Louis?
I haven't even been looking yet.
Okay.
Let me ask you a question in the meantime. Okay. If I may. So at the end, you've repeated some quite interesting but far-reaching claims about what you aim to achieve. A lot of which is dependent on people in your team not making mistakes, right? Because you can replicate it many times over, but if there's an error in there and you replicate it many times, that might be a vulnerability that can be exploited. So can you talk a little bit about what you do to ensure that that's not happening? I mean,
absolutely, functional verification. So, one of the fundamental problems with blockchain networks today is that they don't use functionally verifiable languages, right? Or these like strongly typed languages like Haskell. And I mean if you cannot create a mathematical proof that proves that your code is perfect and will behave in exactly the way that you have claimed it will, then you're really not building something that is fit for financial applications, in my opinion. But I think we can, certainly not for, if this is a public resource, the potential losses are absolutely catastrophic, right? They're open-ended. So yeah, so we just use formal verification for everything.
Other questions? There's one in the back. Two in the back.
Thanks. First of all, thank you very much for the talk. You mentioned at the very beginning business dependency. I think that's what you called it, right?
Yeah.
Business. Absolutely makes sense. You don't want to be dependent on another company doing your own business. But at the same time, on the one hand, you have dependency. On the same time, it somewhat gives you security as well, right? If you are a company, or let's say if your IT department within the company is dependent on a trusted partner, such as AWS, for instance, this business relationship can really be seen also as an
asset. Exactly.
How can you, how can DFINITY provide that?
That's a great question, and it's great that it comes after the question that we just had, because for one, because DFINITY is fully automated, we don't, and it's decentralized and replicated, we don't have downtime. Like, downtime is not a thing in DFINITY's world. It's 100% uptime. So no matter how good your relationship with AWS, and don't get me wrong, they provide an amazing service, right? Yeah. You're gonna have downtime. With DFINITY, zero downtime. Right. The other thing is that we can make these claims because all of our claims can be mathematically verified, because all of our code is mathematically verifiable. And that is one of the primary kind of values, I think, that come along with actually achieving a robust information infrastructure, is not having to take the word, is not relying on relationships, human relationships. All of these failures are human mistakes, right? 90% of data breach is a human error. I remember my dad, right? He swears by his relationship with his bank. Sadly, well, it used to matter. These days, it doesn't matter at all, right? The bank just looks at the numbers. They've got to be able to justify their actions, and they've got to be able to respond to KPIs. And those relationships are no longer relevant. It's happened to banking. We need to bring that to our information infrastructure. And business relationships, sorry. Oh, and there's one other thing that I could tack onto that, and that is that if you build a service on DFINITY, you can build it in such a way that it is formally verifiable and its behavior is fully known. And so we can kind of do these financial service provisioning internally, inside DFINITY. I mean, this is one of the amazing things that Ethereum has shown us we can do through smart contracts and the ERC20 standard.
So if everything's, if things run smoothly, yeah. What if there's an issue and I'm a business? Who do I call?
Great question again. So the thing is, DFINITY will never fail. Its whole job is to not fail. It has one job to do, right? I mean, that's the entire pitch. If your application that has been deployed on DFINITY has a bug in it, what we've realized, or what we've come to terms with, is that we're going to need a huge organization to provide you with support in order to fix this bug and get your application up and running again, especially if it's a financial application. And so we have this kind of term, the NASA for decentralization, that's been quite, people have been making fun of us. But I actually quite like it, because it does convey what we're going to have to do. This is not just a technical task. It's an organizational one as well, where we have to build a massive technical team that understands the needs of all of these different businesses that want to use our platform and can help them in resolving problems through a decentralized governance solution, which I didn't discuss at all in this talk. But
there is a question online. That follows up with a good online question that someone asked, which is from George. Could you explain the governance system? Maybe you don't have time to explain the whole one, but
we can skip through it really quickly, I suppose.
And how DFINITY will evolve as we evolve.
Yeah, that's. I came prepared for that one. So, social consensus. So, one of the big things about blockchain networks is it doesn't matter if you have this amazing kind of economic or whatever kind of consensus mechanism. It just lives on top of a social consensus, right? The fact that we as a society or as a group agree that we will abide by the data or will accept the data held in this system, and so we need a governance system, and this must enable us to determine the behaviour of the network, do all this stuff here. So we have one. It's called the blockchain nervous system, and basically it gives you the ability to make a proposal to DFINITY. And that might be to upgrade the protocol, it might be to freeze undesirable programs or fix broken programs. Proposers might be protocol developers who are upgrading the protocol, concerned citizens who might not like a program that is running on DFINITY. They might find it to be morally reprehensible, and it's important that their culture be represented there. And businesses using the platform might have their own ideas. Also, we might have machine actors. This is this idea of the AI as law. We may wind up with machine actors that have the ability to make specific optimizations. And the way this works is by... this is great. So I just whipped these up, and they're pretty rough, but... So a participant can place a deposit, say a voter, can place a deposit with an extremely long, a bond with an extremely long unbonding period, say a year or something. And a proposal can be made, but you've got to pay a fee or a bond, possibly dependent on the acceptance of that proposal in order to submit one. And the way that we vote on these proposals is through an opaque liquid democracy model, whereby, and this is likely to change the very specifics of it, but say you can vote based on the neurons or the participants in the actual voting system can vote with a vote weighted against the size of the deposit that they made. And they can vote using follow relationships. So say this is a proposal that is tagged protocol upgrade, then they will refer to the protocol upgrade experts in order to get this proposal, in order to not have to vote themselves, but refer their vote to an expert who can actually do this. If the proposal is passed, it gets sent to a super user module, which is really just like a smart contract on DFINITY, and that super user module can execute the proposal with unique permissions. So it has the ability to upgrade the proposal, upgrade the protocol, freeze undesirable modules that are running. It can, and it can change the state of a particular module if it has the permissions to access that particular module itself. So that's how we upgrade the protocol and stuff.
Yeah, another question?
Yeah, so what's the actual current state of DFINITY? Can I deploy an app to DFINITY?
Not yet, but we will have a testnet up within months. I can't give a date. But just to throw, something at the wall, 3 months, the testnet should be up.
Okay, and could I also use, for example, this random number generation then inside an Ethereum smart contract and use the random number inside there?
You could. The way that you would do that is probably through a relay mechanism. I would imagine that something like X relay, the Joseph Chow's like BTC relay, how he was doing. Maybe a system like that you'd need to use, but it might be hard to use that with Ethereum. I'm not 100% sure, but you'd use something like that.
Right, thanks.
Are there any more questions?
I'm thirsty. I'm really thirsty. Should we?
Yeah, maybe it's a good time to get ending words.
Yeah. All right. Cool. Well, thanks, guys.
Yeah, thanks everyone for coming. There's still beers in the back and Morris will come soon with the pizza. Yeah, thank you.